Alright, moving on to the next chapter, and that is chapter 18, Patterns and Matching. Patterns are a special syntax in Rust for matching against the structure of types, both complex and simple. Using patterns in conjunction with match expressions and other constructs gives you more control over a program's control flow. A pattern consists of some combination of the following: literals, destructured arrays, enum, structs, or tuples, variables, wildcards, placeholders. These components describe the shape of the data we're working with, which we then match against values to determine whether our program has the correct data to continue running a particular piece of code. To use a pattern, we compare it to some value. If the pattern matches the value, we use the value parts in our code. Recall the match expressions in chapter 6 that use patterns such as the coin sorting machine example. If the value fits the shape of the pattern, we can use the named pieces. If it doesn't, the code associated with that pattern won't run. This chapter is a reference on all things related to patterns. We'll cover the valid places to use patterns, the differences between refutable and irrefutable patterns, and the different kinds of pattern syntax that you might see. By the end of the chapter, you'll know how to use patterns to express many concepts in a clear way. Okay, so this chapter seems like a reference just to how to use patterns and matching. They introduced patterns to us in chapter 6, so this is still kind of familiar to us, but at the same time, I'm curious to see what they have to say. Moving forward. All the places patterns can be used. Patterns pop up in a number of places in Rust, and you've been using them a lot without realizing it. This section discusses all the places where patterns are valid. Match arms, which, yeah, we've seen this before. As discussed in chapter 6, we use patterns in the arms of match expressions. Formally, match expressions are defined as a keyword, match, a value to match on, and one or more match arms that consist of a pattern and an expression to run if the value matches that arm's pattern, like this. That was a long sentence. Anyway, they basically said, here's the match, here's the value that we're trying to match with, and then here are the patterns that we're trying to match it against. And if any of these patterns hit, as in they coincide with the value, we use this arm, or the expression here associated with it is going to run. Chapter 6 covered that. One requirement for match expressions is that they need to be exhaustive, in the sense that all possibilities for the value in the match expression must be accounted for. One way to ensure you've covered every possibility is to have a catch-all pattern for the last arm. For example, a variable name matching any value can never fail and thus covers every remaining case. So here they're rehashing some of the information that we already know about match, which is it has to be exhaustive, as in the value that passes in, the patterns that you try to match against have to cover every possibility that value could be, which is exhaustive by definition. However, sometimes, a lot of times, there are cases where the exhaustive nature of this might be a little too expressive, let's say. Like there's too many cases to write down, and sometimes you just want to write down a catch-all for everything else you didn't really think about. And I think they're going over what that catch-all is next. A particular pattern, underscore, will match anything, but it never binds to a variable, so it's often used in the last match arm. The underscore pattern can be useful when you want to ignore any value not specified. For example, we'll cover the underscore pattern in more detail in the ignoring values in a pattern section later in this chapter. Okay, so they touched on it. There's the underscore pattern, which will match against anything. You typically put that at the very end when you want to ignore things. And they're going to cover that in the ignoring values in a pattern section later in this chapter. Understood. Conditional if-let expressions. In Chapter 6, we discussed how to use IfLet expressions mainly as a shorter way to write the equivalent of a match that only matches one case. Optionally, IfLet can have a corresponding else containing code to run if the pattern in the IfLet doesn't match. That I did not know. It makes sense, but I did not know that. Also, they introduced IfLet in like Chapter 6, but I didn't really understand the best way of writing it, so hopefully this will clear things up for me. Listing 18-1 shows that it is also possible to mix and match IfLet, else if, and else IfLet expressions. Doing so gives us more flexibility than a match expression in which we can express only one value to compare with the patterns. Also, the conditions in a series of IfLet, else IfLet arms aren't required to relate to each other. Okay. Pretty much what they're saying here is that we have patterns IfLet, which we've already seen, that can be in tandem with else if and else IfLet. So you can seemingly just create a string of like if statements that if this isn't true, else if, things like that. The code in listing 18-1 shows a series of checks for several conditions that decide what the background color should be. For this example, we've created variables with hard-coded values that a real program might receive from user input. And let's read through this real quick, see what they have here. I see a main, I see some variables at the top. We have favorite color. Is Tuesday, false. Age, which is a result, looks like it has to be U8 once parsed. And then we have the IfLet, else IfLet, and then within here we have an if, we have an else, and we have an else here. I see. So the basic structure is, if this is true, do this. If that's not true, try to check to see if this is true. If that's not true, check to see if this is true. If this is true, look at these if statements, but if this is not true, this is the catch-all. Okay? And then we have let some color equal favorite color. Else if is Tuesday, which we know it's not. Else if let age, okay, because it's a result. And I skipped over this one, but some because it's an option. And if age is greater than 30, print this, else print this, and then the final catch-all. So let's write that out real quick. Or I could just copy. I could just copy it over and put it into my editor. And I think I have you here. And that already has a main. And let's see. And it ran to completion using purple as the background color. And just to go through real quick, let's see why I did that. So it got to the first statement, right? If color equal favorite color, color is none, so that's not true. Is it Tuesday? Nope, that's not true. Age does exist. And age is 34, which is greater than 30, so we got to here. So just for the hell of it, let's make age 29. This we see a different option. Now we got to here. But one last thing, let's try this catch-all. So I guess for a result, can it be none? No. It doesn't have a second type. It doesn't have a second type. I'm not sure how to change this. Unless I put something here. Let's see if this works. I mean, sure, that's not going to work like that. So let's make this an option, change things up. None, and then make you sum. And there we go. We finally got to the last line using blue as the background color. Had to change a few things, but meh. Catch all right there. All right, moving on. Let me make this bigger. If the user specifies a favorite color, the color is the background color. If today is Tuesday, the background color is green. If the user specifies their age as a string and we can parse it as a number successfully, the color is either purple or orange, depending on the value of the number. If none of these conditions apply, the background color is blue. So after reading that, it sounds like I could have just made this something that breaks up when parsing. So if we go back to the result which they had here, put the underscore they had there. They originally had 34, right? 34 dot parse. And this was an OK. Is it capital? And let's just run that to make sure it's the same. It is. So if I made this something that couldn't be parsed, let's make it my name, Marcus. Something that can't be parsed, and we get the final catch-all. That was a quicker way of doing it. Glad I read that. Oop. So going back. This conditional structure lets us support complex requirements with the hard-coded values we have here. This example will print using purple as the background color, which we verified. You can see that the IfLet can also introduce shadowed variables in the same way that match arms can. The line IfLet OK age equal age introduces a new shadowed age variable that contains the value inside the OK variant. This means we need to place the if age greater than 30 condition within that block. We can't combine these two conditions into IfLet OK age equal age and age greater than 30. The shadowed age we want to compare to 30 isn't valid until the new scope starts with the curly brackets. That was a lot of words, but I got what they're saying, and that is why the code looked weird earlier. I just didn't say anything. So here, what they're saying is that, here's the example. This IfLet, right? In this IfLet, we introduced a new variable called age, and it's a shadowed variable. It's more or less just the value of the inner age. However, at this point in time, I think it just says if it's okay or not, because it says that on the same line, we can't add the conditional. The conditional has to be within the scope. And what were the exact wordings again? Introduces a new shadowed age variable that contains the value inside the OK variant. This means that we need to place the if age condition within that block. We can't combine these two conditions. The shadowed age we want to compare to 30 isn't valid until the new scope starts. All right, this last line is what was important. So even though this age should be the value of the inner OK, this last statement says that the value isn't valid until we get to the inner scope. So it's only within here, these brackets, that age is actually the number that was parsed. The downside of using IfLet expressions is that the compiler doesn't check exhaustiveness, whereas with match expression it does. If we omitted the last else block and therefore mishandling some cases, the compiler would not alert us to that possible logic bug. Okay, so here what they're saying is that when you use the IfLet and all the other if variant patterns together, right, the compiler doesn't force you to be exhaustive in your checks. So if you were to miss a case, the compiler is not going to yell at you. And we can verify that right now just by getting rid of this else block and running the code again. So if you notice, nothing was printed out. And we're still in the state where we were supposed to go all the way to that else block. But since that else block is no longer here, we seemingly just went through all those checks and nothing happened. And the reason that is allowed is because it's not exhaustive. If this was a match expression, then we would have got a compilation error right at this point when we try to run it. While let conditional loops. Similar in construction to if let, the while let conditional loop allows a while loop to run for as long as a pattern continues to match. The example in listing 18-2 shows a while let loop that uses a vector as a stack and prints the values in the vector in the opposite order in which they were pushed. Okay, here's the vector, which is the stack, pushing 1, 2, and 3, while let sum top equals stack.pop. I see. Print the top. So we're just milking the stack, like popping it one by one off the top. Which, yes, that does go in the opposite order. Yeah, but we can verify it. Okay, yeah, we can. Move that over. Just really quickly. Ugh. So one thing I've noticed when copying and pasting code, if it comes out ugly, you can just use cargo format and voila, everything gets pushed over. It's nice, it's beautiful. And let's run this. 3, 2, 1, and just like they stated, it popped everything out in the reverse order that things were pushed into the stack. This example prints 3, 2, and then 1. The pop method takes the last element out of the vector and returns some value. If the vector is empty, pop returns none. The while loop continues running the code in its block as long as pop returns some. When pop returns none, the loop stops. We can use while let to pop every element off the stack, off our stack. So yeah, going back to here, what they're talking about is this line right here. So while this is not none, if this was none, then the statement is no longer true, so it evaluates to false, and thus the while loop does not continue. It doesn't run the inner block. But as long as something is here, as in when you pop something off and it's a value that is not none, this will continue to run. That seems pretty straightforward. Moving onward. For loops. In chapter 3, we mentioned that the for loop is the most common loop construction in Rust code, but we haven't yet discussed the pattern that for takes. In a for loop, the pattern is the value that directly follows the keyword for. So in for x and y, the x is the pattern. Listing 18-3 demonstrates how to use a pattern in a for loop to destructure or break apart a tuple as part of the for loop. Okay, so we're going over for loops, which was mentioned in chapter 3, I guess very briefly. So here we have a vector with A, B, C. And the reason why it's a tuple is because once we're iterating over it, we're calling enumerate, which will then return the index of the item that we're currently looking at. So for example, this would be index 0, 1, and 2, at least seemingly. But to verify, let's run it. Let's run it. Move that over. Don't need you. Cargo format. Make it look pretty. Run. A is at index 0. B is at index 1. C is at index 2. That's exactly what they have here. We use the enumerate method to adapt an iterator to produce a value, and that value's index in the iterator placed into a tuple. Okay, that first sentence is really wordy. What they're saying here is that we have the iterator, right? This is going over the elements within the vector, and enumerate adds an element to what you're getting back in return. So instead of just getting one element, which would be the A, you're getting A in the index, which we did see. And because you're getting two items, it's a tuple as the return value for the for loop. So you have to specify it. And the first one's going to be index, and the second one's going to be value. And if you didn't know which one was which, you could just print them out to screen and figure it out. But yeah, that's the way it gets ordered. So yeah, that was that first sentence. The first call to enumerate produces the tuple 0a. When this value is matched to the pattern index value, index will be 0 and value will be a, printing the first line of the output. I see. So they're trying to say this is a pattern. I'm kind of hesitant to say this is a pattern. They're placing values to names. I don't know if this counts. I don't know if that counts. Moving onward. Let statements. Prior to this chapter, we had only explicitly discussed using patterns with match and IfLet. But in fact, we've used patterns in other places as well, including in let statements. For example, consider this straightforward variable assignment with let. Let x equal 5. Okay? Throughout this book, we've used let like this hundreds of times. And although you might have not realized it, you've been using patterns. More formally, a let statement looks like this. Let pattern equal expressions. Okay, yeah, I guess that counts. In statements like let x equal 5 with a variable name in the pattern slot, the variable name is just a particular simple form of a pattern. Rust compares the expression against the pattern and assigns any name it finds. So in the let x equal 5 example, x is a pattern that means bind what matches here to the variable x. Because the name x is the whole pattern, this pattern effectively means bind everything to the variable x, whatever the value is. Sure, yes, let x equal 5. Got it. To see the pattern matching aspect of let more clearly, consider listing 18-4, which uses a pattern with let to destructure a tuple. Okay, multivariable assignments, let x, y, and z equal 1, 2, and 3. Here, we match a tuple against a pattern. Rust compares the value 1, 2, and 3 to the pattern x, y, and z. To see, here, we match a tuple against a pattern. Rust compares the values 1, 2, 3 to the pattern x, y, z, and sees that the value matches the pattern. So Rust binds 1 to x, 2 to y, and 3 to z. You can think of this tuple pattern as nesting 3 individual variables patterns inside it. If the number of elements in the pattern doesn't match the number of elements in the tuple, the overall type won't match, and we'll get a compile error. For example, enlisting 18-5 shows an attempt to destructure a tuple with 3 elements into 2 variables, which won't work. Okay, that will give us an error. Let x, y equal 1, 2, and 3. So the big takeaway here is when you want to destructure a tuple, make sure the left side has the same number of variables as values exist on the right side. So there's 3 here, x, y, z, 3 here, 1, 2, 3. There's 2 here, x, y, 3 here, 1, 2, 3. That's a no-no. All right, moving onward. And, we can look up the compile error. Attempted to compile this code results in this type error. Mismatched types. Expected tuple with 3 elements, found one with 2 elements. That is very straightforward. And they even give you the types, integer, integer, integer. That's good. If you want to ignore one or more of the values in the tuple, we can use underscore or dot dot, as you'll see in the ignore values in a pattern section. If the problem is that we have too many variables in the pattern, the solution is to make the types match by removing variables, so the number of variables equals the number of elements in the tuple. Okay? So the underscore pattern to match something that to just ignore a value makes sense. It's just the empty placeholder. However, this dot dot thing, I have no idea what that is. No idea. But I guess we'll find out later in this section. Function parameters. Function parameters can also be patterns. The code in listing 18-6, which declares a function named foo that takes one parameter named x of type i32, should by now look familiar. And here we go. Function foo variable i32. Code goes here. Yes, that looks very familiar. Moving onward. The x part is a pattern. As we did with let, we could match a tuple in a function's arguments to the pattern. Listing 18-7 splits the values in a tuple as we pass it to a function. And that's what they have here. Okay, print coordinates, a reference to a tuple x and y. And then we have, they should be a reference to a tuple of i32, i32. And I guess they're saying that this is the pattern and expression. And then we can just pass in the point. Sure, that counts. This code prints current location 3, 5. The values, point of reference, or the values ampersand 3, 5 match the pattern ampersand x, y. So x is the value 3 and y is the value 5. We can also use patterns in closure parameter lists in the same way as in function parameter lists, because closures are similar to functions, as discussed in chapter 13. At this point, you've seen several ways of using patterns, but patterns don't work the same way in every place we can use them. In some places, the patterns must be irrefutable. In other circumstances, they can be refutable. We'll discuss these two concepts next. Okay, this was a pretty easy section. If you liked it, hit like on the video, subscribe possibly. Outside of that, till next time, peace.